Hello, ladies and gentlemen. Today we're going to be talking about applications of quadratic functions. So basically what we're going to be doing is looking at how we can use quadratics and parabolas to help us represent different things that are kind of real world scenarios. Now, when we walk through this today, I'm not really going to be going through every single kind of example you could possibly see. It's impossible for me to show you, hey, here's all the different things, all the different ways that a quadratic can be used to represent what's going on. Instead, what I'm going to do is kind of talk you through some of the strategies and some of the things that you want to think about whenever you're doing one of these application problems. So kind of like, hey, here's what you want to think about, here's what you want to look for, here are the things that are going to help you kind of set off and see what you're trying to find. Let's go ahead and let's start with an example here. So this is example number one we're going to be talking about. So in this example, we have a baseball that's hit at a point 3 feet above the ground at a velocity of 100 feet per second at an angle of 45 degrees. The path is going to be represented by that function that's listed right there. Okay, so we see the function right here. When h of x is the height of the baseball and x is the horizontal distance. So they're telling us that the function is representing the height of the baseball, and the x value, the inputs that are going in, is how far out the baseball is. Okay? We're going to need to find the maximum height of this baseball and where the baseball is hitting the ground. So the first thing you want to think about when you're thinking about this function or any of these functions is sort of what does your parabola kind of look like for this quadratic function. Because whether it's one that is upside down and sort of forms an arch, or if it's one that's kind of the regular side we're used to that looks like a U, that kind of is going to change what you're thinking about when you're solving for things about this problem. The way you can tell what shape that's going to be is based off the leading coefficient. If the leading coefficient is positive, it's our more traditional U, whereas if it's negative, it's going to be more that arch shape or the N shape that we're used to, that we've seen before. Okay? In this instance, it's negative, so I kind of know that my parabola is going to be more of this sort of upside down shape, this N shape. Okay? Which kind of makes sense. If you think about a baseball, when you hit a baseball, it's going to go up to a certain point, and then eventually it's going to come back down and kind of form this sort of arching motion. The maximum height of the baseball, what the maximum height is, well, we can kind of see that's going to be somewhere around here. And in fact, we actually already know what that point is. It's the vertex, okay? And we've talked about that. The highest point of your parabola, if it's upside down, will be the vertex, whereas if it's the normal U shape, it's going to be the lowest point is at the vertex, okay? Knowing that that's where that point is, I'm going to go ahead and find the vertex, and the y value of my vertex is going to be what that maximum height is, seeing as our y values, or h of x, is the height of the baseball. So I'll go ahead and do negative b over 2a to find out what that, or where that maximum height is going to occur, and then plug it in to figure out what the maximum height is. In this instance, that's going to be negative 1 divided by negative 0.0032 times 2. Okay? And if we go ahead and we plug that in and we calculate it, we're going to get that that value is 156.25 feet. And again, you just put that in your calculator and figure it out. You should get around 165.25 feet. So that is our location where the graph is at its highest point. Where does that occur? It's right there. So then what do I do from there? Well, now I'll go ahead and I will plug it back in to figure out what the height will be for that point. So I'll say, okay, I'm basically going to be finding what h of 156.25 is, which will be negative 0.0032 times 156.25 squared plus 156.25 plus 3. And then I'll go ahead and evaluate this, and that will tell me what the height is, which for our case here will be a height of 81.125. So the height, the maximum height, okay, we'll call it the max. Max height is going to be equal to, a little bit to right here. The maximum height is going to be equal to that 81.125 feet. Okay, again, how did I find that? I know that the highest point of this parabola is going to be the vertex, so I went ahead and I found basically the y value for my vertex, and that's going to be my maximum height. Okay, so by picturing it, thinking about, oh, where's that maximum height going to be, that can help me go ahead and solve for what they're asking me for in that problem. The second part is they want to know, where does the ball hit the ground? So after I hit it, it's going to go up. At some point, it's going to come back down and hit the ground. We're going to assume that the ground would be when it goes back to 0, and that's going to kind of fall back on finding the roots of our parabola. So we're basically going to set this equal to 0, and then solve for what the roots of our parabola are going to be. So we all know how to find roots, so we can go ahead and we can do that on our own. I will tell you that with these application problems, you're rarely going to find one that's going to factor and be really nice. They could, right? I could set you up in a way that they are, okay? But if they're not, it's kind of a nice, the easiest way to do it is to fall back and use the quadratic formula. So here's what I want you guys to do. I want you to go ahead and pause the video. I want you to plug this into the quadratic formula, right? Your A, your B, and your C value. And I want you to tell me where that ball is going to hit the ground, and we'll come back and we'll look at that together. So go ahead and do that, and we'll come back and look at that in one moment. Okay, if you did quadratic formula, you should have ended up with two answers. One of them was negative, and one of them was positive. Okay, the positive one is the one that you want, right? The negative one is going to be, it's like negative 1 or 2. It's really small. That's kind of like over in this area over here of your graph, and that's not really going to be where our function lands, right? Over here, that's where the other root is, and that is where our baseball is going to be landing, and that should be at about 315 feet. I got like 315.47. Depending on how you round it in your calculator, you might be a little bit off from that. As long as you're pretty close to that, that should be what you got, okay? So that's one example of an application problem they may ask us to do. Here's another example. We have a local soft drink manufacturer, and this is a function for their daily production cost, okay? What we need to do is we need to figure out how many units they should produce to yield a minimum cost. What's the lowest cost, okay? So once again, I want to think about this function and say, all right, is this a parabola that's opening upwards, or is it one that's opening downwards? What kind of is going on with my parabola? And what I want to do is I want to, again, look for that leading coefficient. Now, this function is actually kind of written backwards. So we want to look for that coefficient that is with my x squared term. In this case, it's positive. So we are looking at a quadratic or a parabola that is opening upwards like this. Okay, and once again, now this vertex, that is going to be my minimum in this one. So when it opens as a U, it's going to be our minimum, which is what we're trying to find. How many units should produce to make a minimum cost? Now, X is the units being produced, C is that cost. They're not asking us what that minimum cost would be. All they are asking for is, what do we need to produce to get to a minimum cost? If you think about it for a business, that would be more important, right? Well, okay, how many things should we do to be the cheapest as possible? That's what we want to do. So what we're going to do is we're going to say, all right, we're going to take that leading coefficient and this one here, and that's going to be our A and B term, and we'll use our negative B over 2A to find the x value for that for the vertex, which is where our minimum point is. So negative b, it's going to be negative 120, so it'll be 120 divided by 2 times 0.075. Okay, and if we go ahead and multiply that, that is going to end up equaling about 800 units. Not about, exactly 800 units. Okay, so if they want to see the cheapest or the best return on their investment, the cheapest cost that they could have, they want to produce about 800 units, all right? If you think about that, why would that be the case? Why would it be cheaper to produce more than less? They're usually with a sort of manufacturing, there's some sort of startup cost, so you have to pay something up front, so you want to be able to produce some amount to make it worth whatever it costs up front. But then after a certain amount of time, you're going to be spending a lot more on materials and on stuff that you might not end up selling, right? So as a soft drink manufacturer, 800 units, that might be the most you're able to sell, that you're making a profit off it. And once you start going over 800, you may not be able to sell those soft drinks anymore, and now it's just costing you more than what you're earning back through your sales, okay? That's kind of two examples. The main kind of tricks you want to do, make sure you kind of like sketch out what's my parabola going to kind of look like, and then kind of think about what they're asking for. If it's maximum minimums, you want to be finding those vertexes. If it's like the landing point for the baseball, that was one where we wanted to find the root. Just some sort of things you're going to see, all right? Thank you all for watching, and I hope you all have a nice day.